Dr. Edward Yang is going to talk to us about high-performance IP lookup with algorithmic optimizations. I guess the simple way of putting it is he wants to make IP lookups as fast as possible in these days of gigabit networking. Dr. Yang is currently a staff research engineer at Xilinx, and his work focuses on algorithmic optimization of packet processing and performance analysis of heterogeneous computing systems. Prior to Xilinx, Edward worked at Huawei, USA, where he was responsible for steering and evaluating designs of packet processing, offload engine, and the cloud engine data center switch. Edward received his PhD in electrical engineering in 2011 from USC in Los Angeles. His work and his PhD focused on high-speed and large-scale dictionary lookup and pattern matching on parallel platforms, including both FPGA and multi-core processors. Prior to his PhD, Edward spent 3 years at USC's ISI, Information Sciences Institute, where he worked on network cryptography, performance, and symmetric key distribution. And on a personal note, his interests include classical music, piano, world history, and classical Chinese literature. So I guess with that, let me go ahead and turn it over to Edward. Edward, please go ahead.
Okay, thank you. Hello, everybody. Thank you, Sridhar, for the great introduction. So, yeah, today I'm going to present a high-performance IP lookup system or approach, which is algorithmically optimized for many good features, novel features. So with that, I'll start. Okay.
No, it's all right.
Okay. So I will start by introducing IP lookup in a broader sense and explaining why, after more than 2 decades of development, IP lookup remains to be a very challenging topic, and what are the existing approaches. And then I'll introduce what I call the combined length infix pipeline search CLIPS, this architecture, and how it is algorithmically different from the previous approaches. Later, then I will describe how we can, based on the basic CLIPS approach, how we can enhance it to handle virtual routing tables, to handle dual stack consolidated IPv4 and IPv6, and to handle fast and easy dynamic updates. I'll follow this with performance evaluation. So IP lookup fundamentally is the longest prefix match. By definition, it is a set of bit vectors. Every bit vector can have length from 1 bit to up to L bits. So it is a set of variable length bit vectors. And L, in this case, for IPv4, the classical internet addressing is 32 bits. For IPv6, it can be 64-bit in canonical addressing architecture, or it can be up to 128 bits in general. Now, once we get this set of bit vectors, for every input, which is the full length input, we want to find the longest prefix in our set that match our input. So this is what we call the longest prefix match. Now, because of the scalability of the internet, the growth of the internet, we are having larger and larger set of prefixes, or these big vectors, to match against every incoming address. So this continuously put a very tough challenge.
Can I stop you for a second? Folks,
sure.
Can everyone please mute their microphones or their telephones? There's quite a bit of background noise that we are hearing. Thank you. Go ahead, Edward.
Okay. So this puts a lot of pressure on this IP lookup engine, because we are having larger and larger set to compare with. Now, in this graph, I show the routing table size, which is the number of prefix entries in the backbone BGP router from 2003 up to today, and also extrapolates both IPv4 and IPv6. So on the top, we see today, if we look at the 2013, the 13 vertical line, today we in the backbone BGP router, we have about 450K entries, IPv4 entries, and we have slightly more than perhaps 10K IPv6 entries. So, but if we extrapolate the growth of the internet, we see by year 2020, we would have more than 1 million entries combined. This million entries, or 1 million routing prefixes, needs to be compared with every one incoming IP address in order to route the packet. In addition to,
hello.
Yes.
Hi, this is Tilan. I have a question.
Sure.
Don't you expect the IPv4 entries to reduce as the number of IPv6 entries grows?
We will expect the number of available IPv4. Well, there is no more IPv4 allocation available. However, if we look at the number of IPv4 entries, they are about 400, less than 500K. Theoretically, if we have a very distributed, a very large internet, we can have up to 4 billion IPv4 addresses.
Mm-hmm.
So there can still be growth in the number of IPv4 entries inside the backbone router. We just have longer and longer prefixes, or wider range of prefix length in the routing tables. But you're right, the growth of IPv4 entry numbers can become slower, and the growth from this graph we can see the growth of IPv6 entry numbers is much faster than IPv4.
Okay, thanks.
Sure. So another challenge, and perhaps more tougher challenge, is the throughput. And if we look at today's backbone network link, we are looking at 100 gigabit per second, which translates with 64-byte packet, about 200 million lookups per second. Now, if we have a large table sitting in memory, then every lookup requires at least one memory access. And if this table is large, usually this memory is in DRAM. So we look at the speed of the memory. So in the graph on the right, I show how the speed grows. We see quite healthy growth in the data rate of memory from SDRAM up to DDR3. However, these growths are for the sequential access data transfer rate. In IP lookup, we usually cannot predict what is the next IP address we are going to receive from a neighbor switch or neighbor router. So that access is usually a random access. If we look at the DRAM and how they handle random or non-sequential memory accesses, the speed is usually proportional to the memory clock, which is the blue bars on the graph. So they do grow, but they grow much slowly. So how can we achieve high throughput large table while relying on as few external memory access as possible becomes another challenge. A third challenge is the transition from IPv4 to IPv6, or to coexisting IPv4 and IPv6. Now, because what we just talked about, the depletion of free IPv4 address space. Now, the new internet population are going to use IPv4 addresses. So in this graph, I show the statistics from Google, which shows the percentage of IPv4 users over all the IP address that their data centers see. We see that the percentage of IPv4 addresses is growing in a very increasingly fast pace. However, right now, IPv4 occupies about 1% of all users. So this is perhaps the worst kind of transition. That is, we are going to have a relatively long time, some estimate from 5 to 12 years, where the number of IPv6 and IPv4 entries in the backbone can be comparable from 1% to 80%. Anywhere can be the IPv6. What this means is it becomes very inefficient if we design any router or any lookup engine with fixed resource allocated for IPv4 and IPv6 separately, because the range of the percentage range is just this too large. So it becomes a challenge to how can we have an efficient resource utilization in a dual stack lookup. There are other challenges, including the virtualized routing tables, which are used more and more in data centers, where a single physical lookup engine would handle from 1,000 to 16,000 virtual routing tables, and it makes the dynamic update more difficult on any virtual routing table without affecting the performance of the others. It also introduced the large number of virtual routing tables also make the table-specific optimization less desirable. Another one is dynamic updates, where we not only want to have average short update time, we want to have consistent update time. We don't want 100 updates to be performed in 1 microsecond, but 101 updates to be performed in 10 seconds. That would make the higher level networking behaviors, that would disturb the higher level networking operations. So, yes.
Can I ask a question?
Sure.
Just so that everyone can be on the same page, since we have quite a few folks who are not sort of networking experts, can you sort of give an idea for those who are not doing IP lookups and networking, where perhaps the techniques that you might discuss in the presentation, what other broad class of problems do they address?
Right. Well, so the techniques that I'm presenting is basically to help solve the IP lookup problem, to make IP lookup as fast as possible, as efficient as possible. But more specifically, the techniques I'm presenting aims to overcome each of these challenges. So we would like to be able to increase the routing table size without relying very much on the external DRAM. We would like to be able to scale the throughput subject to the available memory technology that permits. We would like to be able to have a single lookup engine where resource can be used very flexibly between IPv4 and IPv6. And this engine should be able to handle virtual routing tables and dynamic updates efficiently. So basically, this is so perhaps if we go to the previous work, over the past 2 decades, there have been many IP lookup solutions proposed, and each has its pros and cons. So the presented solution here hopefully can solve most of the pending issues in a scalable IP lookup solution. Right, but so let me let me just go into a quick introduction of the previous work, IP lookup. So if we look at one simplest way for IP lookup is to search by pattern. So for each routing prefix, if we encode its pattern with a prefix followed by don't cares, and we order them in priority from shorter prefix to longer prefix, then using TCAM we can compare one after another, compare by pattern to see what is the longest prefix that matches. Yes. Is somebody trying to ask a question? Okay. So I'll just continue. If anyone wants to ask a question, feel free to unmute and let me know. So this is the TCAM approach, and the advantage is it's very simple concept. But the disadvantage is this comparison circuit against all the patterns is usually expensive and limited size, and it's usually power hungry, which limits the speed, and it lacks the length flexibility. For example, if I have a TCAM which is 32-bit wide, then it takes a lot of special circuit to use that for a 128-bit pattern match. And the last is it's actually quite not so easy to update. For example, in our table here, we have grouped the lengths very nicely in different priorities. Suppose now I want to add another 5-bit prefix. Then I have to make the priority 5 slot from 2 to 3. There is no way if this table is very compact, or we have to waste some space by over-provision. So a similar but more efficient way is the search by value, where we convert every prefix into a value range, like the graph below, and we organize all the range boundaries in a binary search tree. So we can, at runtime, we walk this binary search tree to find out what is the smallest range that our incoming address falls within. The advantage is, by using this, it takes log L levels or log L memory accesses to perform each IP lookup, which scales nicely if the table size becomes large. The disadvantage is because now every boundary has to be a longest prefix length, because it's a 4-size big factor to describe the range boundary. So we would end up using larger memory, and a binary search tree, in all cases, it's actually difficult to update, even if we use a dynamic search tree. Okay. Now, there are another approach is to search not by pattern, not by value, but by length. And we can have a linear search by length, which is the try approach. So we start in from root, which is 0 length prefix, And for every bit, we go either left child or right child, depending on whether this bit is 0 or 1. There are some variants. We can have a fixed stride multi-bit try. In this case, we have the orange lines. Between two orange lines, it's a 2-bit stride. We can also have variable stride multi-bit try, which would be the some people also call it radish tree or Patricia tree. Or we can have a memory balance try, where some nodes are pushed to a lower level so that the total memory across all levels are roughly balanced. Now, the advantage is that this is a very simple construction. It's usually faster than other construction. However, the disadvantage is we can have up to L levels of, or we can have up to big OL levels of tri-nodes, which makes the lookup latency high. Perhaps a larger number of memory accesses are required. And it's more expensive to pipeline it or to guarantee a throughput. In the case of radish tree, where we have variable stride multi-bit try, the update becomes more difficult if we insert a branch within this within the middle of any stride. So this usually gives us a table-dependent performance. So the last prior work I will discuss is the search, another search by length, but here it is a binary search by length. So here, suppose, imagine we have prefixes length from 1 bit to 32 bit. Now for every length, we can group all the prefixes with that length and put them into a subgroup. We can then, if we can search all the lengths in parallel, then we can find any match in any subgroup, and we can pick the longest length subgroup that match to be our longest prefix match. We can do better by doing a binary search in this length. So we start from length 16, which is in the middle of 1 to 32 or 0 to 31. If we find a match in 16, that means potentially we can have a longer prefix match. Then we go to 24. Now if we don't have a match in length 16, then we go to the table for length 8. So this actually works very nicely, because if we look at the number of levels, we also have only big O log L levels. And it presents a very nice parallelism across different levels. So it can be, potentially can be pipelined. However, the disadvantage of this is we have so many different lengths. And some of them, so for example, 24 is a very popular length in IPv4 routing tables. So some of these tables can be quite large, and some of them are very small. Now, this makes the resource management or resource allocation very difficult. If we pre-allocate resource among different lengths, if later, because of the, if we add, for example, a virtual routing table which has significantly different distribution in length, then our solution may not be optimized. So, and the various number of different tables also make the hardware approach much more complex. So this is where we sort of following the prior works, the trace of prior work, where we propose clips or combined length infix pipeline search. And Yeah, this work was initiated while I was a PhD student at USC under Professor Victor Prasanna. And it basically tries to address most of the challenge, well, all of the challenge that described above, and hopefully in a reasonably good way. And the design goals does include all these 5 points, including we want logarithmic bit O log L in both prefix length and table size lookup latency. We want the architecture to be easily modular, simple, and pipelineable. We want it to be able to handle dual stack IPv4 and IPv6 virtual routing table and can be updated easily. So from the hardware point of view, from architecture point of view, from very high level, the Eclipse architecture, when we map it to FPGA, is a multi-phase approach. So we have from the top to down, we have phase 1 and phase 2, 3, etc., and a tail phase. So we would like to make the phase 1 small and phase 2 to T-1 also relatively small, and they would access the on-chip memory, whether it's distributed memory or the block memory on FPGA. The last phase, the tail phase, we would like to make it larger, so most of the data structure can be accessed from the tail memory, and they are stored in off-chip DRAM. From algorithm point of view, this multi-phase approach, every phase is performing a different lookup or a different match operation, compare operation. So in this case, I am using 64-bit IPv6 as example. So in phase 1, so for any 64-bit IPv6 routing address, in phase 1, we will take the first 32-bit to see whether it matches any 32-bit pattern in phase 1. It's a fixed width comparison. If there is a match, then in phase 2, we will take the next 16-bit. So together, we are covering 48 bits, but we only need to match the next 16-bit against the set of 16 bits stored in phase 2. So if in phase 1 it doesn't match, then we reduce the size from 32 to 16. So from here we can see this is like a binary search tree structure. However, the binary search is in prefix length. And another nice feature is that whether we go from one phase to the next, whether we go to left, that is, whether we go to a shorter prefix or we go to a longer prefix, in the next phase, we always have the same pattern length to match against what is stored in the phase table. So this gives us a very pipelinable and very modular architecture to work with.
Edwin?
Yes.
So in the previous figure or the previous related work, you mentioned that because most of the prefixes are /24, memory imbalance can happen. So in the case of IPv6, 32 and 48 are dominating. So have you, I mean, is any remedy taken to alleviate that issue?
Right. So if you look at here, if we add, so this is the phase table construction process. Now, if we have a 32-bit prefix, in phase 1, this prefix will not be present in phase 1. The prefix or the big factor that will present in phase 1 are those prefixes that are longer than 32-bit. So, for example, let's say we have a 32-bit prefix. So when we match against phase 1, we won't find it because it's not longer than 32-bit. So we will go to phase 2, reduce to 16-bit. And in 16-bit, we will find that it matched the prefix, 16 prefix of this 32-bit. So next, it goes to 24. And we will, in 24, we will find that it matches 24. We go to 28 and 30. So the 28, the phase 4, 5, 6 altogether in this design will be merged as the 8-bit LPM. So after phase 3, after we match 24, we go to 8-bit LPM, and we will find the 32-bit in this 8-bit LPM. So yes, I guess to answer your question, we can have most prefixes at length 32, but in that case, those prefixes will be stored in phase 4, which is the last phase. And the nice thing about this is we store phase 4 in external DRAM, which has very large size. So I guess, am I answering your question?
Yeah, I guess. So, but still, so you have 32 at the top, right? And you have 16 and 48 in the second phase. But in both those phases, you have a certain table that does the lookup, right? A table or binary search tree or whatever mechanism you use, right?
Yes. Yes, you're right.
Yeah. So between 16 and 48, 48 will be larger, right? Much larger than 16.
Yes. You're right. So the number of prefixes in 48 could be much more than the number of prefixes of 16. But they both share the same resource. So it doesn't matter whether we have more 16-bit prefix or more 48-bit prefix. We can fully utilize the resource in phase 2. There, however, is resource provisioning required when we look at phase 1, 2, 3. The relative resource among 1 and 2 and 3. So there are some static resource allocation required. But usually this allocation is much less sensitive to different routing tables because, for example, phase 3 is the sum of 8, 24, 40, 56 prefix lengths. Now the sum of 4, unless we only have very long, so due to this summation, the resource utilization of phase 3 is relatively much more stable than if we take every length as an individual table.
Yeah, so I mean, basically, you have to sacrifice routing table updates a little bit to get this compact representation, right?
Actually not. We will see later that
okay.
The update. Yeah.
So I have a question on that.
Yes.
One. So the 32-bit that's like a host address in IPv4, right? Is that the correct thing that I must assume?
Could you speak really slowly? I couldn't.
Is this for IPv4 addressing or IPv6?
Oh, so this example here is for 64-bit address, so it would be IPv6.
Okay.
Yeah. Yeah. I'll describe how we can have dual stack IPv4 and IPv6 together, side by side.
Edward,
Yes.
Edward, 1 second. There's a question from Will Groves. Will, are you on? Can you ask the question, or do you want me to ask it?
Sure, I can ask it.
Okay.
So the question was, so how many addresses are in each of the virtual routing tables in the tree that you showed? I mean, just approximately how many addresses are in phase 1, for instance?
Right. So the number of addresses in phase 1 depends on the number of actual routing prefixes that are longer than 32-bit. However, it will be depend on somewhat the tree structure. So if we have a tree which has very large fan out beyond or before 32, and all the prefixes are very long, then phase 1 can have a large number of prefixes. But normally for internet routing tables, we have pretty good aggregation. So the number of prefixes, for example, after 32-bit can grow exponentially. In that case, phase 1 would store only a small amount of common prefixes of those longer prefixes. I guess without looking at the actual routing table, it is difficult to say for sure, but in most of the cases that I have seen, phase 1 usually contain very small portion of the memory, total memory. Right.
Okay, yeah, thank you.
Sure. So here, this part 1 basically explains in more detail how the binary length search is performed. So in every phase, we will match the prefix up to some prefix length. If it is success, then we go to the next phase where a additional longer prefix length plus a match ID will be compared. If we fail in the current phase, then in the next phase, a fail ID will be concatenated by a shorter prefix and to be compared. So this is basically how the binary length walk in this page can proceed. So, for example, for IPv4, in phase 1, we will the prefix length, routing prefix length we cover is up to 16-bit. That is, all the prefixes longer than 16-bit will be covered in phase 1. In phase 2, we will cover prefixes from 9-bit to 16, or all the prefixes longer than 8 but shorter than 16, or from 24 to 31. And in the tail search, we will do LPM, longest prefix match, across the 8-bit range. So similarly for IPv6, we also do this binary division. How the actual pattern width, so in different phases, is actually the same. Well, we actually only have one pattern width in each phase. So in IPv4, for example, we have 16-bit pattern width in phase 1. We have only 24-bit pattern width in phase 2. For those prefixes that are shorter than 16, we will concatenate, or we will prefix a 16-bit file ID in front of the 8-bit prefix, shorter prefix. Now, similarly, we do this for IPv6. So by doing so, we can ensure that every phase handle only a single bit vector width or bit vector width comparison. So the architecture can be modular and easily pipelined. Now, within each phase, we can have binary infix search. So recall from the previous part, we have the same pattern width in each phase. So the infix search actually becomes quite simple, and this is something that there have been many different ways to do. If we have a set of fixed width big vectors, how do we find a match? We can use a binary search tree, or we can use a hash table. There are many different approaches, and we can optimize our approach on the particular hardware platform that we have. Now, the infix search process basically describes the same thing, except in addition, every phase gives an output, which is a pointer, which basically is the match ID or file ID, which points to the subset of infixes to be searched in the next phase. So at the end of this clips, we will reach a point where it is no longer efficient to divide the prefix to shorter length. So for example, when we are at a point where we are matching prefix of 8 bits or shorter, then it really doesn't make much sense to divide the 8-bit into 4-bit and to 2-bit and to 1-bit infix. So in that case, we could use a single 8-bit longest prefix match to match the tail for a range of prefix length. So we call this a set of tail infix, or a tail infix set. Now, every tail infix set is a set of prefixes, covers a set of prefixes with length from multiples of 1 plus multiples of 8 to the next multiples of 8. And all these cover prefixes, they should have a common prefix among this within the set. Now, so we also have some example for IPv4. We have 4 in the tail search. We can have 4 different tail infix sets of 4 different lengths. So if we narrow down even more within one phase and with the comparison or the match from the input against any infix could happen like what is described in this picture. On the above, it is, let's say, phase I, or this could be phase 1 in a 32-bit IP lookup. So in this case, we have the input bit 15 to bit 0 as so we have a 32-bit input address. We take the first 16-bit, bit 15, and to bit 0 to match, in this case, in a binary search tree against all the prefixes or infixes stored in this phase. If we find a success, then we go to the right side where we take the next 8 bits of the input, which are bits 23 to 16, and match against the infix stored in that phase. If we fail in the phase 1, then we take the shorter prefix of the input, bit 7 to bit 0, and match against a different set of infix in the next phase. Now the important thing here is all these different sets of infixes in the next phase can be stored in the same memory structure. There is no resource provision required to separate them. So within each phase, we can actually have excellent memory utilization. Okay, so now based on this basic clips approach, we look at how the clips can be enhanced to handle or to overcome the challenges that we previously mentioned. And one of them is the virtual routing table. So suppose we have a 16-bit virtual routing table ID, which means we could have up to 64K different virtual routing tables. Now with clips, there are two methods which can be used to handle this. One is to simply prefix this VID in front of every routing prefix. Now for IPv4, that makes our new or extended routing prefix 48 bits instead of 32. With IPv6, it makes the extended prefix 80 bits instead of 64. But once we have done this extension, then both can be solved in a similar way as the original clips, except in each phase we will match a slightly longer infix pattern. A second method, and perhaps more interesting method, is we could actually introduce a head phase or a phase 0 for virtual routing table ID match. So, for example, for IPv4, we could first perform a 16-bit or how many bit there is virtual ID match, and then go through the 3 phases of the original clips. For IPv6, we could do the same. So by doing so, it makes our solution very extensible in the sense that we can have almost the same solution for virtualized or non-virtualized IP lookup, except the virtualized version, we have a very small table. In this case, only 64K entries at the front. Now, a more difficult challenge is perhaps dual stack IPv4 and IPv6. So the best way to explain it is to just use the previous picture that we have seen, the different phases, and what are the lengths that each phase could cover, what are the prefix lengths each phase could cover. So if we look at this, and as I said, this whole picture is for 64-bit IPv6 lookup. We find that the purple square towards the left bottom half is actually the solution for 32-bit IPv4 lookup. In other words, we could have the same architecture, the same hardware, except the IPv4 addresses will start from phase 2 to phase 3 to phase 4, or the tail phase only. And the phase 1 will only be touched by IPv6 lookup. Now, note that although the IPv4 is covering only the left half of the prefix length, in terms of resource utilization, the IPv4 lookup can still utilize all the resources in phase 2, 3, and 4. because the infix lengths on the left half and on the right half are actually the same. So, and last, we look at how this can be enhanced to perform dynamic update. And actually, if we look at the original, the basic clips, it is very similar. The lookup procedure is very similar to a ordinary try lookup, in the sense that in phase I, we compare a fixed length input pattern against a set of fixed length pattern in the table. And we either find a match where we go to the right side, or we don't find a match where we go to the left side, for example, in this picture. So for dynamic update for insert, basically we still perform this lookup. But if we find any missing infix at any phase, or a marker, which basically means we have a longer prefix than the length that our lookup phase is covering. So if we use our routing prefix to insert for lookup, and if we add any missing infix or marker into the data structure in each phase, then towards the end, we could dynamically allocate memory in each phase. That's either in a tree, dynamic tree, or in a hash table. This has been known how to. We know how to do that. Then we can easily insert prefixes incrementally into the clips architecture. The only the only thing that we need to be careful is if we are inserting a marker, then if there are shorter prefixes of this marker in the routing table, then we have to mark this marker. But this process is just the same as inserting a prefix into any try, where if we insert, if we walk the try, then along the path we will find all the shorter prefixes that we have gone through. So the same principle can be utilized here to dynamically insert prefix into the clips. Now for delete, it's slightly more complicated because when we find the in each phase, when we find the infix that we want to delete, we can only mark it as a potential candidate for removal, because we cannot really remove an infix inside any phase until all its children infixes in the later phases have been removed. So perhaps we could have one way is to have a counter associated with every infix to count how many children are in the later phases are depending on this infix. But more easily or more efficiently is to have a shadow try on the control plane, which find out whether or when any infix can be actually removed. Now, although this requires a shadow try, but this process is actually the same when we want to remove a prefix from a try. We cannot remove a node until we are sure that all its children nodes have been removed. So I guess the conclusion is the original clips can be dynamically updated, and the update cost is update complexity is no more difficult than update a basic simple try. However, it has shorter update time because there are only log L number of levels. And unlike try, it doesn't change the pipeline structure very much. There are always 3 or 4 phases, whether we insert or delete prefixes. Okay, so last, I'll quickly go through the performance evaluation that we have done. We implement the prototype for IPv4 only on Vertex 6 FPGA, and it's running at 156 megahertz, which using dual port distributed RAM and VRAM gives us over 300 million accesses per second. To support this in 2 stages of DDR memory accesses, we use 6 16-bit DDR channels. Each one sustain at least 100 million accesses per second. So in 2 stages, every stage sustain at least 300 million accesses per second. The utilization, we use only less than 5% of the slices. We use more VRAM, block RAM, almost 3/4 of the block RAMs, and almost 2/3 of the I/O pins. So the capacity is, well, so as I said earlier, there is some static resource allocation required across different phases, and in this case, we have only 3 phases. So the capacity of any prefix that's shorter than 16-bit is 64K, which covers 100% of all possible prefixes of those lengths. The capacity of prefixes longer than 24 is 1.5 billion, which covers 9.4% of all possible IPv4 addresses of length longer than that. And for the tail phase, we have 3 different coverages for 3 different prefix lengths. So in our implementation, we can cover up to 7 million prefixes, IPv4 prefixes, with length from 25 to 31. Although this is only 0.2% of all possible IPv4 addresses, but 7 billion is already way more than what we expect to have until maybe 2020, year 2020. The throughput is 312 million lookup per second, correspond to 156 gigabit per second. And latency is very, actually it's a very crucial part, because we designed this FPGA to be, we intend this FPGA to be an outflow engine for IP lookup. Now the outflow latency is limited by the primary data path, by the queue length in the primary data path. So we would like to have as few latency as possible. In our prototype, with quite conservative design, we achieve about 490 nanosecond lookup latency. And that includes actually 2 off-chip accesses to the DDR. Each one, we estimate about 100 nanosecond access latency. So compared with the try-based approach, whether Radix tree or Patricia tree or multi-strike try, this latency is actually very good. Okay, so I guess I am reaching the end of this presentation, and if there is any question, please feel welcome to ask. Thank you.
Thanks, Edward. Let me at least kick off with one question here, which is if you didn't, apart from, if instead of implementing it in FPGA, if you were implementing it in sort of the more traditional architectures, can you discuss the pros and cons of that, and perhaps did you do that study as well?
Yeah, right. So that's actually a very interesting question. If we look at this graph, now on FPGA, the pros on FPGA is that we can quite easily pipeline. This can be quite easily pipelined. Phase 1, Phase 2, Phase 3, Phase 4 in a pipeline manner. So this fits to not all the lookup algorithm or search algorithm can be nicely pipelined. So this fits the FPGA quite well. But on the other hand, we could also have a run to completion model on any multi-core processor, where a processor core will handle phase 1, 2, 3, 4, all of them from start to end. And multiple cores accessing a memory through a relatively large cache to hide the memory latency. So there is no reason that why this wouldn't also do pretty well on a multi-core based system.
Well, in particular, I was thinking about something like CUDA, where I know, for example, that at least for graphics, etc., the guys, at NVIDIA, for example, they use that for, I guess, bypassing some of the traditional inefficiencies associated with multi-core. So I was wondering whether there is some particular aspect of CUDA that might be particularly appropriate for you guys, as opposed to using custom FPGA implementations.
Yes, I think the mapping from Clips to CUDA will be a more challenging, task. I believe in general, it is not very easy to, even for the binary search tree, it is not very easy to map a very large-scale binary search tree to CUDA efficiently, especially if the input is random, relatively random.
Okay.
So, but there might be novel ways of mapping Clips onto this GPU type of architecture. I guess we have to study more to understand.
Okay. One final question. Do you, what's the state of implementation of this technique? I guess this is the state of the research. Are companies working on this in terms of implementing this in their production routers, etc.? I mean, so can you talk a little bit about where it is in terms of being productized?
Right. So initially, as I said earlier, this research was initiated when I was at USC, studying under Professor Victor Prasanna. And I don't think this approach has been productized. Well, to my knowledge, I don't think this has been productized in any existing product. I do feel that this is a very promising approach, and I believe there are students at USC looking at further enhancing this approach and add more advanced techniques. So from this rather prototype or high-level analysis, I feel that, well, as I said, this is very promising, and perhaps there are someday it can be productized or will be utilized. Yeah.
Thank you.
Sure.
Any other questions, folks? I know, I guess Weirong is on the line, and I wondered whether he had any questions about perhaps relationship of IP classification, which he talked about in the month of October, and perhaps your lookup problems that you're talking about now. Okay, I guess Weirong doesn't want to ask any questions. Okay.
Right.
Anybody else have any questions? Okay, if not, thank you very much, Edward,
Thank
for a very informative presentation. I think if there are no further changes to the slides, I'll be uploading them online momentarily, and also the recording. As a matter of information for us to improve these seminars, you'll actually get email about your feedback. Please send them. Please fill it out. Do send feedback because that helps me tune the seminars, etc. Our next seminar actually will continue in this line of IP classification and using a particular brand of mapping algorithms to custom hardware and implementations. And I think Edward's advisor, Professor Victor Prasanna, will be talking next month on February 22nd. So with that, I guess thanks all for attending, and thank you, Edward, again, and see you all on February 22nd. Bye-bye.
Thank you. Bye-bye.